Okay. Am I audible and all? So just checking. Can anybody just unmute and let me know?
Yes, you are audible, sir.
Thank you. All right. Let us do a little bit of hypothesis testing. Just finish up, just do some more examples, etc. And then what we will do is that I'll give you a very high-level view, right, of A/B testing. Right. There's a lot of subtleties, and we'll sort of look at some of the subtleties. Right. By the way, just to sort of tell you upfront, the slides for A/B testing I've not made it myself. I have taken them from I mean I'll give you the references, but at the source the slides are from a tutorial that the Microsoft people had at KDD, which is one of the premier data mining conferences. But I'll give you the references. Okay. So let's get started. So just to remind, and my slides are visible, right? Yes, okay. Slides are visible. Okay, thank you. Thank you, Aditya. And here's the attendance code. I'll flash it once more. But I mean, again, I have written to some of you about the lack of attendance. Some of you have sent me emails clarifying things, and we have taken all those into account. But please be serious about this and also fill in the attendance. I mean, if you're attending but not filling in the attendance, you'll have a hard time deciphering it. Right? Okay. So again, just to remind you what hypothesis testing is, that we want to make these important decisions. See, until this point, right, we've really been talking about processing of data, right? How to build different models, how to sort of, do different kind of prediction. But the important question is, one important part that we have not so much talked about is coming from data to decisions, right? Now, I mean, how do we do that? And that's the entire point of hypothesis testing. That's what I've been stressing, right? That we want to know the that if you're saying that that this is the probability of a head of a particular coin, right? And I want to know say something about, okay, is this how much do I trust this particular judgment? And specifically, let us boil down to slightly more sort of qualitative-ish statements. Just by saying that, I want to say that if this coin is fair, as simple as that. I don't even want the exact probability. Right? I mean, I don't care if it is 0.5 versus 0.7 or 0.5 versus 0.9. I don't know. Right? I mean, I want to say that if it is 0.5 or not 0.5, right? And how can we do so? And similarly, I'll give some examples that I have two different subpopulations. Let's say that, another question that people ask is that let's say in industry, let's say software industry, right? Do women get paid on an average less than men? Right? Is that I mean, that's a valid question to ask, and that's something, because that says something about a gender disparity, right? So how do we test that, right? In a statistically significant manner. Another one that we have been sort of discussing, and that is very important to all of us, that has been very important to all of us because of the pandemic, is that how do you test the efficacy of vaccine? We all heard that all these vaccines, the India vaccines and as well as the non-India vaccines, the Covaxin and others, they were, I mean, even after they've been created, right, they had been in testing for a long time before they were actually given approvals. So why did we need that, right? And this also then leads to, I mean, maybe I should not make so much controversial statements. If you look at the kids vaccine now, right, has that also gone through the same kind of significance testing to understand its efficacy? Two things to understand its efficacy. Number one, to say that whether it is having any negative effects potentially on any small subpopulation. Right? Has it gone through the same kind of testing? These are the things you should look at. You should try to understand it if you're a data scientist. Okay, and just to remind you, we're saying a hypothesis, right? Here is how we frame it. There's a population, right? Ideally, if I had infinite resources, right, we would sort of ask everybody in the population, and then get the answer. That is, of course, not possible, just because of the fact that it might even be infinite. and versus there is a sample that you're taken in the population, and we can collect data on the sample. We can collect and we can test the vaccine on the sample. We can sort of calculate the average income of the sample, etc., etc. We want to argue about the population, but we only are relying on sample-based estimates of these parameters. Very important, right? And hypothesis is a statement about the population parameter, not about the sample parameter. We want to say something about the population parameter. So, by the way, please feel free to unmute anytime and ask questions or make comments. Okay. I find this online mode very hard to teach in because I'm not looking at all of you. So please feel free to unmute. Okay, so here's a standard terminology. We are saying that let's call theta to be a population parameter, and theta could be anything. Right? Just as of now, let's just say that it's a number. Right? We're not talking about theta to be a vector of parameters. It's a single parameter. Let's say that, for instance, it's a probability that the fund will give high. And we have two competing hypotheses that we make a judgment on: null hypothesis versus alternate hypothesis. And these are two different statements about theta. Because they're complements of one and they're complements of one. So it won't be that some, I mean, that some as, I mean, it won't be the case. So H union HA covers the entire range of theta. That's what I mean. So then again, we're talking about some subtleties in choosing the null hypothesis, right? And one subtlety that's in the last line out here is that it should be the case that the null hypothesis shouldn't. I mean, there's a computation aspect to this. The null computation slash statistical aspect of this, right? In choosing the null hypothesis, because the null hypothesis, I need it to be something that under which I can make the following calculations. I can say that if the null hypothesis is true, right? If the null hypothesis is true, then what is the probability that theta lies in this particular range? What is the probability that theta takes this extreme value? I should be able to make these kind of statements, right? Either by appealing to central limit theorem, by appealing to explicit closed forms of the distribution under the null hypothesis, or by doing simulations assuming the null hypothesis. That should be the real rigorous sort of way of choosing the null hypothesis. That's one thing. Another way of choosing the null hypothesis is that it should be the case that the alternate hypothesis is the one, right, that for which in order to believe that you should need enough evidence, right? That should be another way of looking at the alternate hypothesis, right? That it should not that somebody gives you a drug, right? With the null hypothesis is that then there is no effect. Right, that I'm acting in a pessimistic manner, there is no effect. If you can show that if you can give me enough evidence that there is an effect, only then I will reject the null hypothesis. See, the two things actually come together in this null hypothesis. Because if in a null hypothesis I say that there is no effect, I'll be able to say that look, if I test it on population 1, if I test on population, and if I don't test it on population 1, if I give population 1 the drug, if I don't give population 2 the drug, then under the null hypothesis, they have the same distribution. Their blood pressure or whatever they're trying to get have the same distribution, because under the null hypothesis, this drug really has no effect. So then I can actually, this satisfies my statistical aspect of choosing a null hypothesis, because I'm able to say that these two populations, the control group will come to the definition of the control group, as well as the treatment group have the same distribution. This also satisfies the other kind of philosophy in choosing the null hypothesis, right? Because only when you show me that there is enough difference between the treatment group and the control group, I'll be accepting, in some sense, I'll be rejecting the null hypothesis that says that there is no difference, right? Only with enough evidence. We'll see a lot of examples of this as we go forward. And we saw this, that suppose we wanted to do quality checks on items, and so theta is the fraction of defective items in the entire batch that we had. I think we had Anant making pencils in his factory, and theta 0 is some threshold, right? And we want to call it a good batch if theta is bigger than, if theta is less than theta 0. So what should be the null hypothesis here? Again, here you can fall back on the philosophical aspect of the null hypothesis, which says that look, only if you can show me that there is enough evidence, this being a good batch, I'll accept that this is a good batch. Right? So that means that I start with a null hypothesis with a negative statement. It says that no, My null hypothesis is that theta, with the fraction of bad items, is actually bigger than theta 0. If there is enough evidence, I'll reject. So therefore, the alternate hypothesis is that theta less than equal to theta 0. This we saw here. In choosing the null hypothesis, the computational or the statistical aspect comes into play. That if I have a coin toss and we're asking whether it is fair, okay, there are of course two possible H0. So a theta equal to half and theta not equal to half. Right? As we discussed, that both of them are not equally suitable as H0, right? Because if you take theta not equal to half or theta greater than half as H0, right, that does not really give me much information, because under the theta, right, it is not clear how to come up with the distribution of the test statistic. Right? Because even if theta not equal to half, it could be that theta is 0.5000001. Right? So then what? How can I say anything? So here the right null hypothesis to work with is that theta equal to half, and yeah. So I mean, again, we have gone over this, lots of caveats about how it gets used. We have talked about the basic framework. That these are the 3 steps, right? That we need to go over. That first, you need to find out what is the test, what is it to qualitatively frame that what is the question that I'm going to answer. Then you come up with the test statistic as well as the null hypothesis together. Right? The test statistic is a statistic that summarizes the data, because we will not be able to talk about the entire data all at once. I mean, because I don't even know the kind of data. Typically, we summarize the test statistic, summarize the data using a single test statistic. Then we talk about that test statistic. Right? For instance, the coin being fair is defined by the test statistic, which is the fraction of the tosses that give you hand and head. Right? The income disparity of the 2 sexes of the 2 genders is given by the average income of the male population, average income of the female population, maybe the difference between them. So we'll see some slightly more complicated statistic. Then you come up with the null hypothesis, and typically these two have to go hand in hand, choosing the statistic and then the null hypothesis. Then you start by presuming the data actually follows the null hypothesis. And then you get that, okay, if that happens, what is the distribution of the test statistic? Then you actually look at the sample, right, that you have collected, the data sample that you have collected, and see that what is the value of the test statistic for the data sample that you have collected. Right? And then you see that does that look unlikely according to the distribution that I had just drawn in step number 1. Right? That if it lies very far off in the tail, if it looks very, very unlikely according to the distribution that I draw in step number 1, you then you conclude the rejection of the null hypothesis. Okay? Let us see. As we were saying, that we had started with some experiments with Gregor Mendel, and I really liked doing this because this was an age, right, where even statistics was sort of getting created. Right, and of course, I mean, this genetics is not being created. So while people did do experiments, right, even before this, I mean, Galileo and others, they had done a lot of experiments. But this is one of the first, I mean, to my limited knowledge, this is one of the first wide-scale experiments that I have seen. Right, and Mendel, 1822 to 84, I mean, who lived from 1822 to 84, was the father of genetics, and his basic idea was that there is something in the cells that carries information from across from parent to child. That is his basic thing. He does not know cellular structure. Right? Does not exactly know what DNA is. There's no concept of that one. But what he's saying is that there is something. There is a unit that carries information across generations. That's his basic thing. And the way he's and his next sort of his next scientific statement is that, well, if I mean, once I have I mean, a father and a mother, right, their information gets mixed up, right, and creates an information and creates this information unit for the child. Right? That's what he's calling the gene. I mean, I don't remember if he actually called it the gene or not, but that's what he's saying, that the information from the father, information from the mother, right, gets mixed up and then gets combined and creates the information for the parent, for the child. Right? And therefore, what he's saying is that suppose I take generation 1, in which there are, I mean, I'm breeding pea plants. He's trying to justify this by breeding pea plants. There are 2 kinds of pea plants that he has. One is that whose flowers are purple, and one is that whose flowers are white. right? And then it takes sort of 4 P plants, right? 3 of them are purple, and one of them is white, right? And what he's saying is that, look, if I take their sorry, I have forgotten the distribution of the parents, but basically we set it up such that at the level that is looking, a random pea plant should have a 75% chance of a purple flower. Exactly. Because the grandparents that he had chosen, out of the 4 grandparents, 3 of them has purple, 1 of them has white, and then he's taking their children, right? And then at that second level, right, at that second generation, he's looking at the statistics of the pea plant, of the color of the pea plant, color of the flower of the pea plant, right? And because each of these had 3 grandparents who are purple and 1 grandparent who are white, then each of these second generation pea plants should have a 75% chance of having a purple flower. Right? If his idea about this uniform mixing from the parents, about the if his idea about the information from the 2 parents being mixed is correct, what he does is that he creates 900 pea plants using the exact same crossbreed, right? A huge field of pea plants, right? Pretty amazing. And then he calculates, this is his test statistic. See, his model, right? That 75% number, that is what is coming up with the hypothesis, right? That is what is telling you the distribution, what the distribution should be, right? Under right? And okay, so just a caveat, what you will see is that I have given you some spiel about null hypothesis can only be rejected, not accepted. He does not exactly work that way, right? He works the other way around, but again, hypothesis testing was nowhere getting formed at this point, was nowhere being formalized. So let's just see what he's done, right? And we'll see the differences to the current. So then what he calculates is that he calculates in the second generation the percentage of purple flower plants, and then he subtracts 75 from them and calculates the difference. Right? And these are the actual plots that it has come down. Somebody has plotted his data and then looked at it. So he runs. So pretty amazing. Look at these numbers. He ran 1,000 simulations, each with 900 plants. He's not applying to CLT. Does not even probably know what CLT is, because CLT was central limit theorem was even getting formed parallelly, right? And this is what he calculates, right? 1,000 simulations, each with 900 plants. 1,000 fields, each with 900 plants. It's like a huge number of plants. This entire army. Okay. And this is what it plots. X-axis is the test statistic. Remember the test statistic. It is that at the second generation, percentage of purple flower plants minus 75. That is the x-axis. And y-axis is that out of these 1,000 simulations, right, what percentage of this value of the test statistic? Right? For instance, in this bucket between 0 and 0.5, what fraction of the 1,000 simulations have the test statistic in this bucket? That's what is plotted out here. What fraction of the test statistic has this bucket? That is what is plotted out here. Right? So this is in some sense the distribution of the test statistic under the null hypothesis. Right? That's what he's done. He's done an actual simulation. Right? And then again he sort of did this. He did a sample. So to say that one of the fields he set aside as a sample, and then he said that let us look at the value of the test statistic on my sample. This is what I call as the actual sample. The others were just sort of the others were just simulations of the null hypothesis. And then he finds that the percentage of purple flowers is 75.89%, right? Which means that the difference is 0.89, which lies solidly in the middle out here, right? Out of 929 plants, he has 705 plants that are there, and therefore it is more or less at the center of the distribution. Which means that it says that look, my hypothesis is actually favoring my model, right? And therefore I think I can trust my model, right? This is what he said. Very interesting. Okay. So let us go in steps. How to test that a coin is fair? What is the test? This is an easy question right here. I won't even bother asking you this question. I'll ask you a harder question. Right? The test statistic is clearly the number of heads. So, okay, actually here there are two options, right? To test a coin is fair, you could have the test statistic to be just the number of heads, or you could have the test statistic to be the fraction of heads. Which one do you prefer? Anybody?
Fraction of heads.
Fraction, why is that?
So number of sample size and fraction of heads does not equal sample size.
I mean, your sound got distorted for just a second there. Could you just repeat again?
The number of heads will depend upon the total sample size. Whereas fraction of heads.
Very nice, very nice. Because the number of heads depends on the sample size. So therefore, I cannot really form a nice null hypothesis in there without specifying the sample size. If I specify the sample size, then yes, I could do it. Then the two are equivalent. But I mean, let's just frame it in terms of the fraction of heads. Okay. So now, so then how should we go about? Let's just see. So H0 is saying that theta equal to half. Let's just write it this way. Like this. Okay. Now, what should I do? How to get distribution of, let me call this Z. No, Z is very, let me call that theta hat. Because Z we are going to use later. Distribution of theta hat under H0. How can I say this? Any thoughts? What is expectation of theta hat under H0? See, H0 is saying that theta equal to half. Any thoughts? How can I get? No? Because see, what is the distribution of theta hat under H0? So, okay, so to do this, let us see that what is the distribution of the numerator under H0? Because the distribution of the numerator defines the distribution of theta. Okay, so let me call that NH. We call that in number of x. So I want to say that what is the probability that NH equal to T under H0? You know this, all of you know this. Yes. So what is the random variable NH? I'm tossing coins and I'm counting the number of heads. What is the random variable? I'm not able to, I was not following the chat fraction of heads because it is a ratio of it. So, so Spandan is correct from my previous question. So what is the distribution of NH? What random variable is it? It is a binomial random variable, right? Because I'm counting, because there are two possibilities, head or tail, right? And I'm saying that then what is the number of heads? So therefore, it's a binomial random, right? So therefore, I can say that this is equal to n choose t, right? T to the power, if h0 says that theta equal to half, t to the power half, n minus t to the power half. This is really the complete distribution of the random variable nh under h0, and therefore, right, the distribution, the probability that the theta hat, which is equal to nh by n, right, equals t by n, right, under h0, is also equal to the same thing. Well, it is just a scaling, t to the power half, n minus t to the power half. So therefore, this is really, I easily can get this, right? Just by dividing, just by scaling nh by n. So then, therefore, right, now I should be able to say that if we observe, right, let's say some number, some alpha heads in n tosses, we can calculate greater than equal, we can calculate how likely it is under x. And circle this. We can calculate how likely it is under x0, right? The observation, the event that happened is that we observe greater than equal to alpha heads in n tosses, and based on this distribution, we can easily calculate how likely it is under x, right? And this is exactly the p-value of the test. Okay, this is exactly the p-value of the test. Basically, the p-value of the test is saying that if the observation that I have actually made from the collection of data, how likely it is under H0, under the null hypothesis. That is the p-value. And if that, and then you come up with a significance threshold, as we said. Some typically used one is 0.05, and say that if that likelihood, that probability is less than 0.05, then I say that, oh, let us reject H0, because it seems very unlikely, because the likelihood is less than equal to 0.05. Right? But this is exactly the p-value of the test for this simple statement. Is this clear? Let's go forward. Questions? Let's go forward and see some slightly more complicated example. Okay? Here is a more complex example. It's a very important one, right? As you will see. That suppose a particular US state is to select jury uniform their rank. You probably know that in certain countries, in our country, sort of the decisions, the legal decisions are made by judges. Right? All the cases are presided over by judges. In certain countries, like in USA, it is presided over by juries. There is a judge, but the jury announces the sentence, right? And whether the convict and whether the person is convicted or not. Okay. And the jury is kind of, it's the technical term is that a jury of your peers. That's a constitutional term. And typically what it means is that you have to select a jury that is fairly representative of the population. Right? And this is to ensure that, the philosophy is that by having a jury that is representative of the population, we are not really biasing against one particular group. Right? Because it's possible that there is some inherent bias about some specific subpopulation, and we should try to take care of not having these biases when we come up with the court judgments. That's why they work with jury. Okay. So now, suppose in a US state, we're supposed to select a jury uniformly at random among the subpopulation, among the population, and we're trying to find whether there's a racial bias. Okay? So So how do we do this? So let us formalize the statement. Right. So what is the data that we have? Number one, right? We have that 15% of the that out of the eligible, out of the people who are eligible to be jury, because not everybody is eligible to a jury. If you go tomorrow and to the US court and announce that no, everybody who steals a piece of bread, I want to announce, I want to send them to jail for 5 years. Right? If you say that this is my inherent belief, you might not be acceptable as a Jew because you are, your inherent belief is somewhat strange. So okay, so then 15% of the people who are eligible to be Jews, right, are Asian. 18% of the population are Black. 12% of the population are Latino. 54% of the population are white. 1% of the population is Asian. Okay? This is this is a breakdown of the eligible population. So now what happens is that every time a jury selection happens, let's simplify. Let's say that the jury size is the same every time you see it, and let's say that there's a panel, this jury panel that is that consists of M people who have been selected from this eligible population. Okay. And there are multiple panels that have been selected, and I want to come up with I want to test for racial bias. I want to say that is the jury selection really being done uniformly, or is there a racial bias in the jury selection? Again, now thoughts. What do you think should the null hypothesis be? What do you think should the test statistic be? More important. Any thoughts? And see, these two have to go hand in hand, because unless you define the test statistic, you cannot say the null hypothesis is. So, thoughts out here. I hope the question is clear. What is the test statistic? What is a good test statistic? What is a null hypothesis? Because see, this is not a coin toss, right? There is a categorization. There's Asians, Blacks, Latino, White, other. So it is not enough for me to test that the percentage of Asians is close to 0.5. I somehow have to test all of these together, right? I have to come up with a single number. I have to come up with a number that sort of combines each subpopulation's closeness to these targets, right? And then combines that all of that into a single number. Any thoughts? Can I call out names? Just speak out, just speak out. 80, Jovi, please speak out, because I might not be able to see the chat. 80, absence of racial bias. Okay, very good. 80 is that there is the racial bias. Very good. So why did you choose that as the 80, Jovi? I think Jovi is on Moon Breath today. Okay, so let me try to prefer an answer, because just because of time, is that allows us to get the distribution of the test statistic. That is one possible way, one possible reason. But now, what is the test statistic? Anyone else wants to take a stab? So here is a test statistic, right? Let us see. That here is what we will do. First, for each panel, right, we will calculate the fraction of members for the ith panel. Let's say we will calculate the fraction of members for each race. Let's say that, oh, okay, I missed out the other fraction out here. Let's say that, I calculate the number of Asians in the panel divided by the size of the panel, number of Blacks in the panel divided by the size of the panel, African Americans, number of Latinos, number of whites, number of others. Divided by this, right? And then what we will do, right, is that we will, now I have a vector, right? And we will average this vector over all possible panels. But suppose I want to test for all the panels together. I have the first panel 1, 2, 3, 4, 5, 6, F6. the 6 panels, and I average them and I get F bar. So now I have a sort of one combined vector that represents across panels. There's lots of issues here. You will tell me what the issues here are. Okay. But suppose you do this. Now what we will do, right, is that okay, we take a random sample, right? So supposing this is the average F bar that you have seen across panels, right? That when you average across all the different panels, you have seen 26% white, you have seen 8% African Americans, you have seen 8% Latinos, you have seen 54% white, 26% Asians, 54% white, and 4% others. This is your observed data. This is the observed data. And now, under X0, he took a random sample. Taking a random sample is easy, right? Because you start out with a population. I mean, you just simulate. I mean, it's nothing else. You start out with a population with this. With this many Asian tokens, this many African American tokens, and then you do take a sample of size M, and then you calculate the fraction. And when you do the random sample, you find out that okay, that this fraction are Asian, this fraction are African Americans, this fraction Latino, this fraction white. This is so. This is really X0 being simulated in some sense. This number is X0 being simulated, right? And here is the same picture, sort of drawn sort of diagrammatically. The same thing drawn diagrammatically. That this is the eligible fraction, right? The fraction of eligible in each category. This is what you have observed. The yellow ones, the yellow bars is what you observe from the data. The blue ones are what you see from the random sample. Now, obviously, they're not the same, right? This column and this column are not the same. But first of all, I mean, how do I mean, these are two vectors. So somehow I have to merge. I have to take the difference between these two vectors and I have to come up with a single number, and that will tell me the difference between the panel observation and the random sample. Right? Let us do that. And here is a common statistic that is used. It's basically the L1 difference between the two distributions, or the half of that. It's also called the total variation distance. Right? It's typically applied only for probability distributions. It says that suppose you have two probability distributions. One of them is 0.1, 0.2, 0.7. The other is 0.05, 0.9, 0.05. You calculate the probability distance. You calculate the difference between the two. 1 minus 0.05 is 0.05. 0.2 minus 9 is 0.7. I'm taking the absolute values. 0.7, 0.05 is 0.65. You sum up these three, right? So that is 0.7 or 1.4. Okay. So this is, and then you do a half of that. So don't worry about the half. That is just to ensure that this value stays between 0 and 1. Right? So this is what the total variation distance between two probability distributions. And you can easily show that these are always between 0, that this is a quantity that is always between 0 and 1. Okay. So now let us calculate the total variation distance. The absolute difference. So this is again the panel observed data across panels. This is the simulation data, right? Sorry. This is the eligible fraction. This is the observation, and for the simulation is not here. So then this is the difference between the two. 0.15 minus 0.26, 0.08 minus 0.1, this difference, and I take the absolute differences and I sum them up. Let's say multiply that, and I get 0.14. Is this just noise? How do I know? Right? Because see, in my coin toss example, I could clearly say, right, that under null hypothesis, this is the distribution of the test statistic. Here it is not so easy because the test statistic is sort of complicated. So what do we do? See, okay, here is what you can do, right? I mean, if nothing else, this is what you should fall back on. Just simulate X0 and find out the PDF of the test statistic. Period. Right? This is essentially, I mean, I can talk a lot of jargon, but this is essentially at the heart of non-parametric tests. Right? Just remember this jargon, if nothing else. Right? Basically, just simulate X0, finding out the empirically the distribution of the test statistic, and find out the PDF of that. This is slightly more computational, but it's foolproof. So then, that means that you sample a lot of panels according to X0. Here might be the distribution of panel I, Then you find out, okay, what is the P eligible minus Q1, P eligible minus Q2, P eligible minus Q2, Q, and the distribution of these values. See, in each of them, when I write the absolute value, I'm really taking that L1 difference, or the total variation difference. And then you find the distribution of these two values. So now, because it's simulated upon H0, this is really the distribution of the test statistic under H0. Right? And now you can go back and look at 0.14 and figure out where exactly in the distribution this 0.14 lies. Does it lie at the center? Does it lie at the tail? And this is the final step of the test, the conclusion of the test. By looking at the distribution of the test statistic and by looking at the observed value of the test statistic, we can conclude if we have strong evidence to reject the null hypothesis. This is really the story of hypothesis testing. Okay, let's see. Right? I mean, again, I sort of I like to give these examples that look. I mean, again, a word of caution. Whatever I have been sort of repeating. When you do this kind of hypothesis testing, right? Strong evidence. When I say strong evidence, that is formally that is the significance of the test, right? And and there are really two possibilities that we talk about. We either talk about reject X0 or we fail to reject X0, right? And just to kind of drill it into your mind, fail to reject X0 is not the same thing as accept X0. And this is where Mendel's statements, formal statements, differ from the statements that we make about hypothesis testing today. Right? Mendel was saying that let us accept this X0. We are saying that no, we fail to reject this X0 versus we reject X0, right? And the way you should think about this is, I don't know if any of you followed the panel that was there in the US elections about, I've forgotten the head of the panel, about the US election of Donald Trump that talked about Russian collusion, right? That sort of tried to look into that whether this there's been Russian collusion in the US elections, because that's a very serious thing. A different country should not really be interfering for or against any president, right? In the internal elections. Right. So then, there was this long panel, right, that went over a lot of proof. Presented proof, etc. And at the end, I've forgotten this person's name. That's very sad. All they're saying is that look, right? We have no evidence that a Russian collusion did not happen. We cannot say that a Russian collusion did not happen, right? So they're not saying that the Russian collusion happened because they don't have direct proof of that, right? They're saying that at the level of proof that we have, we cannot say that the Russian collusion happened because we are not able to present direct proof of that, but we are not really clear of our suspicions, right? We are saying that we are not saying that the Russian collusion did not happen. We are not giving a clean sheet. That's basically the same as what we're trying to say. That what we say is that we fail to reject H0. That is not the same as accept H0. For instance, if we say that H0 is that drug X does not increase blood pressure, right? Fail to reject H0, accept H0 would be to say that okay, drug X, drug X does not increase blood pressure. I have kind of proof of that. Fail to reject on that is that maybe I don't have enough data. Maybe it increases blood pressure, but only by a small amount. It's just that with this statistical test, I'm not able. I fail to reject this statement. Important point. The failure to reject H0 can happen because of many reasons, right? It can happen because you have not collected enough data. It can happen that because the effect is so little, right, that you cannot really say anything about this. Right? So that's why you have to be a little careful in here. Okay. So just to sort of go forward, the significance of the test. Right? Okay. So when do we reject H0? So typically there are two things. There is something called something called the critical region of the test statistic, right? And then there is something called a p-value. See, basically these two are interlinked. You should think about critical region. The definition of critical region is basically that that once you have the distribution of the statistic, you say that these are the regions, right, in which it should not it is unlikely that the test statistic will appear in these regions, will take a value in these regions, in these intervals, right? Because if it takes a value in these intervals, that's very, very unlikely, right? And that I will reject as strong evidence. That is the definition of critical region. For instance, if the pointers, I mean, in the pointers example, you could define the critical region by saying that if I obtain more than, let's say, 800 heads out of 1,000, right? That is my critical region. Associated with that is the p-value, saying that the probability of appearing in this critical regions is less than 0.05. That is the significance level of the test. You define the critical regions is the same as defining the significance level of the test, right? The significance level is basically the probability of appearing in these critical regions. So the p-value of the test is then the chance that that based on the modeling, the null hypothesis, the test statistic equals the observed value as we observe in the sample, or even further in that direction, right? Because sometimes it's not an exact value. It says that okay, that's what we define as the p-value. That the test statistic takes value bigger than 0.05, bigger than or less than 0.05, or bigger than 100. That's what we call as the p-value. That it sort of lies in, that I define a sort of threshold that says that okay, the test statistic being, let's say, bigger than this quantity, or the test statistic being smaller than this quantity is very, very unlikely, and that is what I calculate as the p-value. The p-value, that's why it's then tied to the threshold that we use, right? The threshold is the critical region. P-value is completely tied to that threshold. So again, very, very important point that people when you try to ask people that what is the definition of the p-value, people will say that the definition of p-value is that the p-value is the probability of the null hypothesis being true. Absolutely wrong. Absolutely wrong. P-value is not the probability of the null hypothesis being true. P-value is that if the null hypothesis were true, the condition of on the null hypothesis, right? That what is the probability of seeing this data, this test statistic equivalently. P-value is what is the probability of rejecting the null hypothesis if the null hypothesis were true. This is the p-value of the significance of the test. Okay? And we say that is less than 0.05. That is why we're saying that is less than 0.05, because we're saying that if the null hypothesis were true, what is the probability that I'm still rejecting it, and I want that to be small. So to operationalize this, again, after choosing the null hypothesis and the test statistic, how to get the distribution, right? In general, run simulations. Feel free to run simulations. With our existing tools, there are more efficient methods. That is exactly why we did the central limit theorem. Okay? Decide what the test statistic is. Decide X0. Decide on a confidence level. A priori. Okay, you should not be deciding on the confidence level later. Decide on a confidence level a priori at 5%. Right? Basically, what that says is that if the data that I'm seeing is only 5% likely, is at most 5% likely under the null hypothesis, then I will reject the null hypothesis. You have to decide that a priori. And then, based on the confidence level, you can immediately, because you have obtained the distribution of the test statistic, you can immediately obtain that what values of the test statistic constitute evidence against the null hypothesis at this confidence level. Right? Basically, it's something like this. Do I have a picture? Yeah. It's saying that suppose this is the distribution of the test statistic. Okay. You say that, okay, my confidence level is 5%. So then you go and then say that, okay, if the null, the area under the curve in this shaded region plus in this shaded region is 5%. Right? And therefore this is my threshold, because if I only am interested in 5% sort of confidence, then I can put the thresholds out here. And if my test statistic happens to fall out here, I can reject the null hypothesis. If it happens to fall out here, I cannot reject the null hypothesis. That's what. Questions? Maybe I'm repeating over and over. So let us calculate the p-value for point fairness. I'm just being very, very deliberate and slow. But let me know if it gets boring. So first of all, there's a tail inequalities. We have not done this in this course, but if you do any solid theoretical machine learning course, if you do randomized algorithms, you'll see these tail inequalities. These are Markov's inequalities, Chebyshev's inequality, some of you might know it, chain of bounds, etc. These give non-asymptotic bounds. Non-asymptotic bounds, which means that if you do n samples, it tells you exactly that what is the probability that the distribution sort of falls. The number of heads is at least this value, is at most this value. It tells you that. Those need a little more assumptions, because those typically are easy to say only for bounded random variables, for 0, 1 random variables, etc. Right? We don't always have them. So we don't typically, the statistics people tend not to use the daily inequalities too much. They fall back on the central limit theorem, which in its limit is the same as the daily inequalities, but it uses lesser assumptions. It works with all random variables, sums of that are bounded and that have finite variance. That have finite variance and finite mean. They don't have to be bounded. They have to have finite variance and finite mean. And theoretically, it is really true for large samples, but it works fine in practice. A lot of observations have been made that if you have sample size of 100 or so, you can say that the central limit theorem has kicked in already. For instance, if I were to calculate if for the coin toss, if x1, x2, xn are the are 0, 1 random variables that say that if I obtained a head in the ith toss or not, you calculate xs as the number of heads, and then either you apply tail inequalities on xs or you apply CLT on xs. See, this is the form in which I can apply CLT, because I have a sum of xs is the sum of random variables, which is exactly the setup in which CLT applies. So let's just see how it would look like, the CLT. So xs is the sum of random variables, each of identical random variables, because I'm tossing the same coin. Let's say that mu is the expectation, so and sigma is the standard deviation. So CLT says that xs minus m times mu divided by sigma times square root m approaches m01. Right? Where mu is the expectation and sigma squared is the variance of x. Under the null hypothesis, right? Mu equal to p, right? P half, mu equal to half, and sigma is also equal to half. So therefore, sigma is sigma is equal to square root p times 1 minus p, because this is a Bernoulli anomaly. So under the null hypothesis, I have the exact, and I say that this exactly follows the n01, right? I say that CLT has already been sort of achieved, right? So therefore, I have the distribution of this random variable, which means that I have the distribution of the random variable xs also. Right? This is what the CLT would. This is what the CLT route for the coin toss would do. For the chain of bound, it turns out that for this simple example, in case you know chain of bound, if not, just shut your ears for a moment. The chain of bound basically gives the same bounds. For this very simple example, it gives exactly the same as the CLT result, which is not the case for the other random variables. So in general, right, we say that if x bar is the sample is the test statistic, x bar minus mu by standard deviation approaches n01, right, and therefore I can get a confidence interval of x bar based on my confidence level, right? That because this is n01, let's suppose I want to look at a sort of confidence level of alpha, right? Now I know that to get a confidence level of alpha according to n01, how far do I have to go in the tail, right? So that's how I take it. So I take that I choose C in that particular manner, and then I will sort of so C will have to be a function of this alpha, the confidence level, and I will define that that this is the region in which I won't be able to reject the null hypothesis, and outside of this region, I will reject the null hypothesis. Just a simple, just couple of slightly more tricky things. That here is the standard deviation of x bar, right? You might not be able to from x0. Sometimes the assumption of x0 itself gives you the standard deviation, as in the coin toss example. Because when I assume that the coin toss probability is p, that already gives us the standard deviation. Sometimes it will not happen, because there might be more complicated x0s, right? Or rather more complicated statistic. So what you do typically is that you calculate the standard deviation by the sample standard deviation. Replace the standard in the denominator by the sample standard deviation, and that works perfectly fine. Yeah. Okay, so now going back, so now you have calculated the under H0 you get the mu, right? From the sample standard deviation you get S, and then you calculate the test statistic as x bar minus mu by s divided by square root m. So m is your sample size, presumably. Okay, and now we say that this approaches N01, that suppose, and where these are the corresponding quantities, and now suppose we observe a specific x1, x2, xn. Okay, and from this you calculate the x bar. So this is the distribution. Right? Now you take a sample x1, x2, xn, and you calculate the x bar from the sample. Okay, so now as I mentioned, that because you know that this variable under H0, right? Under H0 should have the mean mu, and anyway should follow the central limit theorem. Therefore, the 1 minus alpha confidence interval under H0, right, will be something like mu minus s times square root m by times z 1 minus alpha by 2, and mu plus s by square root m z 1 minus alpha by 2. Okay, so this should be the confidence interval for this should be where x bar lies, right? If H0 were true, right? Similarly, you can flip it around and say that if H0 were true, then mu should lie in this interval, right? Because if x bar lies in this interval around mu, that's the same thing as saying that mu lies in this interval around x bar, right? Because it is just saying that x bar is bigger than or equal to this quantity, therefore mu is less than or equal to x bar plus this, and x bar is smaller than or equal to this quantity, therefore mu is less than or equal to x bar minus this. So therefore, the 1 minus alpha confidence interval for mu is this interval. Okay, and by plugging in, it depends on what is alpha, right? For instance, if you take alpha equal to 95%, I know that for the normal distribution, you should take z 1 minus alpha by 2 equal to 3. This quantity becomes 3. Okay, and I get an explicit interval. So now, deciding again in this setup, right? Deciding whether coin is fair. We did this. We calculated this distribution either by doing the central limit theorem or by doing the simulation, and then I say that look here. Suppose I say that the test statistic is something like this. The statistic is fraction of x minus half, right? That means that here the test statistic is how different is a fraction of x from half. So that means that here the low values are favoring H0. If this value is small, then that is an indicator that you cannot really reject H0 because H0 is saying that it is equal to half. It is fair, and the high values favor rejecting H0, and therefore. And in particular, if you're interested in a 5% sort of confidence interval, right? Then you say that okay, let me do 2,000 losses. I'll do 2,000 losses, and I work at 5% confidence interval. You can figure out that using that normal distribution, the boundary that you should draw out here for 5% confidence interval is like I don't remember what this boundary is. It's like 45. Let's say it's like 45, and therefore because this is fraction of x, so 1045, I think it is like 0.05%, 0.05, and therefore yeah, 0.05, and therefore if you obtain 1045x, right, you say that I actually lie in this region rather than in the middle of the distribution, and therefore I could potentially reject x0. So this is how we work out. The p-value of the test is in the probability of seeing at least 1045 hits, right, under x0, and you work it out using the. You don't need to do a simulation here because now we are doing the central limit theorem. You're assuming that the number of heads is following the central limit theorem, and then you find out using the table of the normal distribution. x bar minus mu by sigma root, then you calculate, and then you find out. You look up, you get the standard normal variable, and then you look up that particular thing. As I said, that if the p-value which is the likelihood of seeing this statistic under H0, right? If this quantity is less than 0.05, we say that I'm rejecting it. Notice that this threshold is entirely arbitrary, right? And also notice that the CLT is just a shortcut, right? I mean, you could always do simulations. The CLT just helps us cut through all this computational overhead, right? But in your mind, it should be that I can always tackle any hypothesis testing using just simulations, how complicated it should be. In this setup, the fairness, what we say is that my test statistic is the total variation distance, right, between two distributions, specifically between the expected proportions, which is the eligible fraction, and between the observed proportions, which is the panel distribution. Right? Between the yellow column and the pinky column, right? That is the test statistic. Now what you say is that, look, I mean, I have observed my test statistic to be this quantity. This is the quantity that I have observed in the data, right? I have observed in my sample the 0.7 or something, whatever you have seen. This is quantity is 0.7. So under X0, what is the probability that this random variable, right, takes value that is bigger than 0.7? That's what you calculate, right? That's what you need to be able to say by applying the central limit theorem. What is the probability that the total variation distance takes value that is bigger than 0.7 if H0 were true? That is, if I was doing a uniform selection. See, you could do this. And you could do simulations. So there is one thing that we are missing when I took this statistic. There is one piece of information I completely dropped. Any thoughts on what piece of information I dropped? One piece of information is not figuring into the statistical test so much. Any thoughts on that?
The alpha value.
Mm-hmm.
Is it the alpha value?
Well, the alpha value, I mean, you will come up with yourself. You will say that the alpha value is 0.01 or 0.05, that is up to you. The piece of information that you completely dropped, see, when you look at this table, and this is this slide is a complete description of the statistical test out here. Do you see anywhere a size of the panel? That is not figuring, right? For instance, consider these two setups. Consider a setup in which the size of the panel is 100 versus a setup in which the size of the panel is 1. So in the setup when the size of the panel is 1, you would expect a lot more noise, right? The distribution should be a lot more noisier than and therefore somehow that should come into it. Because if I'm taking 100 samples from population, I should be more representative of the population than if I'm taking one sample from the population. Using one sample from the population, it can never be really significant. So therefore, there's a better statistical test for this particular setup, and that is called that takes into account the sample size, right? And that is called the chi-square test. Right? It is applied in these categorical settings where the data is count, right? For instance, you say that look, I mean, let us not worry about the fractions. Let us not normalize by the size of the panel a priori, right? Let us say that every panel consists of members from K classes, the Asian, the African Americans, Latino, white, others, and I have my data is the number of counts in each panel. I will normalize it, but in a slightly more sort of clever way. Right?
So we're going to have to keep changing the statistical test depending on the nature of the problem, right?
We are going to absolutely. But the one thing you will have to change the test statistic based on nature of the panel. But the basic thing remains the same, that you have to come up with an H0, and at the end, you assume that your test statistic after the normalization follows the central limit theorem. These two facts remain the same. But I mean, what is your test statistic? That depends on the nature of the problem.
But then the alpha value can just be taken as something like as you say 0.05 or something like that.
Yeah, I mean, because see, once you have normalized your test statistics so that it's a standard normal standard normal variable, right? Then the alpha, I mean, the 0.05 makes sense. That's why it's stuck to 0.05, because we always normalize it so that it becomes a standard normal variable.
Okay.
That's why people have stuck to 0.05. But as I'm saying that, I mean, I'll show you some examples why the 0.05 is very, very, I mean, you should not overinterpret it in some sense. I mean, it's a good thing, but you should not overinterpret it.
Okay.
Okay, so now, I mean, here we're doing a different test. The same setup, we're doing a different test. I mean, in my data, I'm not normalizing by the size of the panel after I, right? My sort of from the H0, right? I can get the expected count in each panel, right? Because if my number of panelists is 1,000, if 15% is Asians, then I know that the expected number of Asians in my panelists should be 150, because 1,000 times 0.55, 150. Similarly, okay. So basically, I mean, for every, I mean, you sample a panel size, and then, I mean, you take a panel size, and for that you calculate the expected number of panelists according to the null H0. And similarly, from the data, you actually calculate the number from every panel. Now what you do is that you look at a different statistic. You look at a statistic that is the, I mean, I won't go too much into it. You look at this statistic. See, what is it? We are saying that OI is the observed data from the class I. This is the sample that you have taken, which is the actual number of panelists from class I. EI is the expected number of panelists from class I, right? So that means that under H0, EI equals the expectation of OI, right? Because that is under H0. If H0 were true, the expected number of panelists from class I means the race I will be exactly EI, by definition. Yeah. So therefore, and now what we do is to say that, look, for instance, suppose number of panelists is 100, is equal to M. So suppose the number of Asians is 26, number of African Americans is 8, number of whites is 54, number of Latinos is 8. Okay. Now what you do is that you calculate a statistic in the following way. You take OI minus EI, observation minus its expectation, take the square, divide by EI. Okay, OI minus EI square divided by EI. Okay. See, why are we doing this? In some sense, this is equal to OI minus expectation of OI divided by its square divided by expectation of OI. So if you share about this a little bit, you will see that this is basically what is known as a chi-square random variable. Because effectively, if I were taking the square root of this, this would be OI minus expectation of OI divided by square root of expectation of OI, right? Which is basically a standard normal variable. A variable minus its expectation divided by its standard deviation. That is a standard. That really, according to CLT, will approach will basically be a standard normal variable, and therefore a square of that. This is the square of that, right? And this will be a chi-square, and this is called a chi-square normal, chi-square random variable, and we're summing up k of them, and this sum has a specific distribution. It's called the chi-square distribution with k minus 1 degrees of freedom. Chi-square distribution with k minus 1 degrees of freedom. Why k minus 1? We're summing up k. Then wouldn't it be natural to have say that this is the sum of these is also a chi-square distribution with k degrees of freedom? Any thoughts on why did we say k square? Because these observations, there is some are not completely independent. there is some linkage among these observations because because the number of classes, if you take the contribution from each of the classes, they have to sum up to the panel size. So therefore, if you give me k minus 1, then the counts of k minus 1 classes, I'll be able to say what is the count of the kth class, right? So that's why there's only k minus 1 degrees of freedom, not k degrees of freedom. Okay, because the sum of all the k classes has to equal n. Okay. So now this is a chi-square random variable with k minus 1 degrees of freedom, and we also know the distribution for this in closed form, right? We know the distribution of this in closed form, and this is the particular picture. We know the expectation of this, we know the variance of this, etc., and we'll be able to now say that, okay, under the null hypothesis, this is the likely region, and this is 1 minus alpha confidence interval region, and this is the critical region. If you fall, which takes up only alpha probability, alpha total probability. So if you fall in this critical region, I will say that I reject the null hypothesis. Okay. So the chi-square test is basically this. We calculate the statistic, which turns out to be a simplification of the previous formula, this particular thing, right? And I did not show you the simplification, it's basically the same thing, just a little bit of algebra. Then you calculate that for the test statistic, what is this quantity? For the panel that you have seen, what is this quantity? And now you look up, the probability of this value for this particular distribution, for the chi-square distribution with k minus 1 degrees of freedom, because see, it has been completely normalized, right? And suppose this quantity is 4, and then you say that, okay, what is the probability of 4 for what is the probability that on to the right side of 4, right? For the chi-square distribution of k minus 1 degrees of freedom. Why are we looking up to the right side? Because we're trying to say that it's not about the value 4 exactly. It's about saying that what is the chance that the test statistic takes the value that I've observed in this data or a worse value than this. So that's why I look at the right side, in that right side. And this is the p-value of the test. Now, this area is the p-value. And if this area is less than 0.25, let's say, we say that reject. If this area is bigger than 0.25, we say that cannot reject. Okay? Remember, the null hypothesis was that it's fair. Okay? So if this area is less than 0.25, I say that look, this is too extreme. There's a huge difference. There's a huge, that if you are really choosing fairly, then the chance that you would see this kind of distribution of races in your jury panel is very unlikely. Less than 5% likely. Right? Therefore, I reject the null hypothesis. Right? Else I say that, oh, perhaps I'm not able to reject this null hypothesis. Any questions? So, yeah. Question? What is right?
So,
yeah.
Yeah, so in this case, we have considered those races to be categorical values.
Yeah, the races to be categorical, and that's why the right test here was the chi-square test, which is dealing with the count values of the categorical races.
But what would we do if they were numerical or something like that?
So what do you mean the numerical?
If they were not categorical, say.
But then what is the see, how does it matter? Perhaps I can understand a question. How does it matter if I call the races to be 1, 2, 3, 4 versus A, B, C, D? That does not matter, right? The entire point was that every race is a category.
Okay.
Right? And there are counts associated with the races.
Okay. Okay.
So what I call the races did not matter at all.
Okay.
What you are asking is that, okay, what you're asking is something like if my this thing did not have to do with category. For instance, I want to say that how close are you to just like in a pointers example, that is not a categorical example, because there what we're trying to say is that how close are you to 0.5? Are you 0.5 or are you not? Are you fair or are you not? Right?
Yeah.
Okay. So any other questions? Let's move on. Again, just go over this. This contains whatever I've been talking about over and over. The start with the null hypothesis, collect some data and decide on the test statistic, calculate from the data, right? Look up the p-value, right? And first of all, you should predetermine the test, the threshold. you should not determine the threshold level after you look at the p-value, because that is called p-hacking. Because you say that, oh, okay, my p-value is 0.1, therefore I say that at 0.1 threshold, this is my threshold, right? That is the wrong way of doing statistics, right? You predetermine the threshold and then you look up and calculate the p-value of the observation under H0. Decide if the p-value is less than this threshold, and if it is, then it is evidence under H0 at confidence level 1 minus alpha. This is a final statement, right? This is the kind of statement you make. That at confidence level 1 minus alpha, I have evidence against X. Specifying the confidence level, we need to say something. So, lot of caveats. Notice that there is that suppose you set the threshold at 45 and decide and reject H0 if the statistic is bigger than 45 for the point toss, however many point tosses you give. There is still a 5% chance of a fair point gets rejected. So important to remember, right? That if the confidence threshold is 5%, there is a 5% chance that a fair point gets rejected, right? And this will be critical when we're doing multiple hypothesis testing. Right? Because if you're testing multiple hypotheses together, there will be a false rejection of 5%. 5% of the hypothesis will be falsely rejected, even though the null hypothesis will be falsely rejected, even though they're true. Okay. So in the statistics, if you wanted to kind of put it up in the false positive, false negative, this is the picture. I mean, again, the same kind of picture as we are seeing for the confidence, for the confusion matrix. Let us take the H0 true, the H0 false, right? Accept H0 when H0 is true. This is a good place to be. Reject H0 when H0 is false is a good place to be. If H0 is false and you accept H0, this is the type 2. This is called the type 2 error, right? And furthermore, when H0 is true, but you reject H0, this is the type 1 error. This is the alpha. This is the alpha that we were talking about, right? This is the one that we control. The type 1 error, basically saying that if H0 is true, what is the probability that I am rejecting it? That is the significance level that you sort of decide, the 0.05. Okay. Type 2 error, we cannot really control. It's called the power of the test. You can try to measure it. It's hard to measure. It's hard to measure because definition of type 2 error is saying that if H0 is false, what is the probability of rejecting? Sorry. The type 2 error is the probability of accept H0. Yeah. Accept H0 given H0 false. Yeah, the power of the test is kind of like recall, right? That what is the probability of rejecting H0 if H0 is false? That is the power of the test. And this is the type 2, the 1 minus the power. Type 2, okay, it is written correctly. And this is hard to make. This is hard because H0 is false does not give us much information. We are saying that H0 is false means the probability of the coin is not equal to half. It is not equal to half. But so what? Right? That does not tell me. I mean, it gives me no way to quantify that what is the probability that I accept H0. You can try to measure it empirically using, but even if you want to measure it empirically, you have to measure for a specific value of the theta. You say that okay, if the probability of the coin is 0.6, in that case, what is the probability that I accept it to be? I still call it fair. If the actual probability is 0.7, what is the probability that I call it fair? I mean, you have to do this kind of stratified kind of measurements, which is quite. Let's do a couple of examples before we finish. Suppose the National Sample Survey shows a nationwide employment of 9%. The CM of a state wonders if this is true in his state or not. He takes a sample of the state residents to see that whether the unemployment rate is significantly different than 9%. Supposing P is the unemployment rate in the state, what is the hypothesis set that is being used? Okay, sorry, this is the hypothesis set that is being used. That H0 is saying that P equal to 0.29 versus HA is saying that P equal to 0.9. So what is under what conditions is a type 1 error being committed? Remember, what is that type 1 error? Type 1 error is the probability of rejecting H0 given H0 equal to 2. Probability of reject H0 when H0 true. By the way, this example is Khan Academy, which is a sort of simple but nice lectures about hypothesis testing. Take a look at that. So which of these is a type 1 error? Which of these are the events? Any thoughts? See, X0 is equal to 2 for type 1 error, right? Which means that I can already nail down, and X0 is 0.09. I can already nail it down to be, it either has to be this or it has to be this, either A or C, right? X0 equal to 2. Only in A or C is the problem, is X0 equal to 2. Now I'm rejecting X0, right? Which means that I'm saying that I'm saying that it is not 9%, which means that I get it to be this. Right? That it says that unemployment rate is not 9%, and it actually is. This is the type 1 error. Clear? Questions? Let's do one more. This is very important in our campus, small campus. There are a small number of restaurants we have seen, and suppose the campus committee also decide whether to open a new restaurant. Is there enough interest? They survey a sample of students, and they say that whether there is, they want to see that whether there is strong evidence that the proportion interested in a new restaurant is more than 40%. Right? They want to see that is in my entire population is the fraction that is interested in a new restaurant more than 40%. If that is the case, the restaurant will be opened, and for that they take a sample and say that in this sample is the fraction that is interested in a new restaurant more than 40%. Right? Whatever statistic that is. So they calculate the fraction out here, and then based on that, they want to calculate this fraction on the interested people in the entire population. Supposing P be the proportion of all students who are interested in the restaurant in the entire. So P is the fraction in the population, right? Which you don't know. Suppose they use the following two hypotheses. See, very important question. They're saying that the null hypothesis is that P less than or equal to 0.4, saying that I maintain the status quo. I won't open a restaurant. The alternate hypothesis, right, is that P is bigger than 0.4. It means that I reject the null hypothesis only if there is strong evidence. Right? It means that I open the restaurant only if there is strong evidence to reject the null hypothesis. What is a type 2 error? Type 2 error is the probability of accepting X0 if X0 is false. That's a type 2 error. Just to remind you, yeah, this is a type 2 error. If X0 is false, then what is the probability that we accept X0? So then, what happens to the decision making if you commit a type 2 error? Anybody? Didn't even get to A/B testing. That's okay. Anybody? And then I'll show you a cartoon, I promise. Then we'll finish. D. Is this Purushottam Mohan? D. So the restaurant is built when it should not be. Okay. Why is that? Let's see. This is a suggested thing. So H0 is false. Right? H0 is false means that P is bigger than 0.4, which means that the restaurant should be built, right? Because in reality, P is bigger than 0.4, but we're accepting H0, right? H0 accept, or rather not rejected, which means that if you accept X0, which means that you think that P is less than 0.4, which means that you do not build the restaurant. You do not build the restaurant while you think that the restaurant should really be built, right? Because P is really bigger than 0.4, right? So the restaurant, the right answer in my opinion, is the right answer in my opinion, let me take this, is this, right? That the restaurant is not built when it should be. It's very important to understand the implications of this type 1, type 2. And therefore, you should be, for instance, here is a very, my last question, and then the carbon. Right? Suppose in airport security check, okay, how can we set this up as a hypothesis test? And what is the type 1, type 2 trade-off? Which one would you like to commit? Because there's always a trade-off between the type 1 and type 2. What would be a security check? Supposing you have this beeper machine, this kind of the X-ray machine, right? Which beeps every time it sees something, and maybe the beeps are loud enough. The amplitude of the beeps becomes higher, right? If if it is more suspicious thing. Well, let's forget the names. So what does how would you set this up as a hypothesis test, and what is type 1 trade-off versus type 1 versus type 2? What is the null hypothesis? What is the test statistic? Would you say specifically, would you say that H0 is person is suspicious, or H0 is that person is not suspicious?
So we would go with the person is not suspicious.
Person is not suspicious. Okay, interesting. Why is that?
The H0 in absence.
Hmm.
That's why I suggested not suspicious.
So if you take H0 to be person is not suspicious, which means that only if you have enough evidence to reject it, only if you have enough evidence, then you're rejecting it. Right? Only if you have enough evidence to be suspicious, are you rejecting it? Are you rejecting this H0? That only, let's say that the blip, the sound of the blip is your test statistic, the amount, the volume of the blip, right? So only if the volume of the blip is very large, right? Perhaps you are rejecting H0. Now you should think about the cost of a false positive versus a false negative. Which of these two errors is more expensive? Type 1 error versus a type sort of a false positive or a false negative? Under
type 2 would be more dangerous.
Right, in your right. Because and type 2 error you cannot really control. Because see, it is much more expensive to let a suspicious person get into the flight than to do extra checks on sort of innocent people. Right? Because the potential harm that we can get by letting a terrorist on the flight is much larger than the inconvenience and caused by doing extra checks. Right? So therefore, the right, now the sort of thinking about the cost benefit analysis, the right H0 here is actually the first one. That my default is that I think that a person is suspicious only if I have significant evidence to the contrary. That is only if the sound of the blip is very, very low, I sort of let this person go, and then I say that I'm rejecting this H0. Right? My sort of if I don't, even if I have not enough evidence, I say that I will do another search. I will do that the person is suspicious. I will assume that the person is suspicious. And that will give me enough handle to control alpha. See, in here, alpha will be if I take this as the H0, my type 1 error will be that the probability of my type 1 error is the probability of rejecting, basically doing extra check. That I reject X0, that I do an I sort of sorry. I reject X0, which means that I say that a person is not suspicious. Right. I sort of let so my alpha now is that the probability I let a person a terrorist get into the flight. That is my P1. That is my alpha. And that is something that I really want the hardcore control on. I want to be able to say that the probability that I let a terrorist into the flight is 1 in 1 million. Right? So that's what I really want to control, the T1, because T2 is hard for me to control. Okay, so that's important way to think about the hypothesis. The type 1 error is that we declare
it's very important to take into the errors when forming the null hypothesis.
Yes. Understand the effect of the type, the false positive and the false negative. What is the real world implication of committing a false positive versus the real world implication of committing a false negative? It's very, so that also comes into the null hypothesis. For instance, as we are saying that here, suppose take the null hypothesis with the person is unsafe. Declare safe only when we have significant evidence against it. Test statistic is a signal metal detector. Type 1 error is that we declare safe, but the person is carrying an unsafe item. I want a real hardcore control on this type 1 error. Type 2 error is that we declare unsafe, right? But while the person is safe, it's okay. I can commit a significant fraction of type 2 errors. I'll just do extra checks. Right? So for instance, false alarms like that. It's okay. I sort of run them again through the metal detector and all of that. Right? So again, think about it for the COVID, what it really means. I'll sort of share the slides. Okay, simple example. So I don't want to take up too much. So here's I've been promising so please, I make the slides available. So here's a cartoon I was promising, and I end with this. Somebody comes to you. So this is XKCD. If you don't see that, you should totally go and read that. Suppose somebody comes to say that jelly beans cause acne. So that they're scientists. Let's investigate. Okay. So now they found no link between they sort of did statistical tests, right? Let's say that they had a set of people eating jelly beans and they find no statistical test. That is the p-value that they get is bigger than 0.05. But suppose maybe a particular color causes it. So now they say that okay, let us test with the purple jelly beans. Let us test with the brown jelly beans. Let us test with the pink jelly beans, blue, teal, salmon, red, turquoise, magenta, yellow, right? And then finally, all of this, and they say that, oh, for the green jelly beans, I find my significance level is less than 0.05. My p-value is less than 0.05. And it comes onto the news saying that green jelly beans are linked to acne. 95% confidence, 5% chance of coincidence. What is the problem in this? Is there a problem in this? Okay. Is the news justified? If not, then what is the problem? Any thoughts? Quick, you can go for tea. I think the rain has now concluded, so we'll do the second session on in class. And there's tea for all of you. I'll just walk up there also. So, any thoughts on this one? And then we'll end in a minute. I refer to this problem in things. Next session time. Okay, let's say, people will need some time to walk in. So 20, let's do like 10, 15 then. Sorry, 11:15. Next session is at 11:15. So this is multiple hypothesis testing, and that's the problem. Because we say that look, because we took a threshold value of 0.05, there will be 5% of null hypotheses that are falsely getting rejected. That are falsely getting rejected. And that's what we're catching. And therefore, if you want to do multiple hypothesis testing, you have to be a lot careful. There's lots of tricks, right? For that, you should look it up. I can give you references. There's something called Bonferroni correction and all of that. You should take a look at that. Meanwhile, you should take a look at these two chapters. There's a data science course from Berkeley. Very nice, very easy to read online textbook they have, and more slides and video are available in this website. So please take a look at this. I'll make these slides available on Discord. Okay. Any questions? If not, thank you very much. We'll see you in class.